So before we move on, let's do this example. Suppose a thermodynamical ensemble has 7 independent particles that have access to 2 energy levels. Determine the number of microstates if the particles are bosons or fermions. Given one particular particle distribution for the system and the associated degeneracy for each level as N1 equals 3 and M1 equals 4, and number 2, N2 equals 4 and M2 equals 6. So in this situation, let's start with the first case, in which case we consider the particles to be fermions. So when the particle is a fermion, so for a fermion, we know the number of ways a single energy level may be constructed is given by Fermi-Dirac statistics. And for our Fermi-Dirac statistics, we learned that there is a limit of 1 particle per container. And we also know that it is given by omega equals m factorial over n factorial m minus n factorial. So knowing these, we can find m factorial divided by n factorial m minus n factorial for case 1 for each energy level. Case 1, I have N1 equals 3 and M1 equals 4. So my for 1 will be 4 factorial divided by 3 factorial, 4 minus 3 factorial, or indeed 4, 3 divided by 3 factorial, 1 factorial. The answer comes out to be 4. For case 2, I will have N2 equals 4 and M2 equals 6. So my second case will be 6 factorial divided by 4 factorial, 6 minus 4 factorial, or 6, 5, 4, 4 factorial, 2, 1, which I can simplify it to just be 15. So this is the multiplicity, which implies that the number of microstates corresponding to this macrostate microstates corresponding to this macrostate when the particles are fermions is omega 4(1) times omega 4(2), which gives me 4 times 15 or 60. Now, what happens if the particles are bosons? So if there were bosons, the number of ways a single energy level may be constructed will now be given by Bose-Einstein statistics. So instead of writing all of that down, I just want to make sure that we understand all of the same words as they were given above by Bose-Einstein statistics. And for my Bose-Einstein statistics, the formula was this one. And there is no limit on the number of particles. So going back, I can write this as n plus m minus 1 divided by n factorial m minus 1 factorial, which implies for the two cases that we have, case 1, n1 equals 3 and m1 equals 4, my omega phi 1 will be 3 plus 4 minus 1 factorial divided by 3 factorial, 4 minus 1 factorial, or 20. Similarly, for case 2, when I have n1, n2 equals 4 and m2 equals 6, this will give me 4 plus 6 minus 1 factorial divided by 4 factorial, 6 minus 1 factorial, or 126. Or the total number of microstates that correspond to this macrostate will be 20 times 126, or 2,520. So, with the limitation of 1 particle per state, I will only get 60 microstates. And when that limit is taken away, the possibilities are 2,520.